So this is section E, question 2. It says how many liters of water can be made? So how many liters of water, I'm going to go ahead and pull out relevant information, can be made from 55 grams of oxygen gas, so we're starting 55 grams of O2, and an excess of hydrogen. So again, anytime you see an excess, don't even worry about it. It doesn't matter. That's just saying that it's not going to impact anything. It says the pressure is 12.4 atm. We know we're using that ideal gas constant. And the temperature is 85 degrees Celsius. All right. So this is also related to the problem that we did in number 1. So number 1 had the equation 2H2 plus O2 reacts to form 2H2O. Awesome. So for this one, we're going from grams of one substance to liters of another. We know that we can't do a straight conversion from there, so we're going to have to use the mole. So we're going to go from grams of O2 to moles of O2. Once we're at moles of O2, we can go ahead and switch compounds to moles of H2O, and then we can get liters of H2O. The most important thing with this gas stoichiometry is that anytime you're going from moles to liters, you have to find that number. It's not just going to be 22.4. So 1 mole equals 22.4 at STP and STP alone. So these conditions that we are at right now are not STP, so we cannot use that conversion. So instead, we're going to find out what the volume is by plugging it in and deciding it. When we have N, what we're going to do is make the assumption that it's 1 mole. This makes it way easier, so in the same way this conversion we normally use the STP, it's 1 mole equals that amount. We're going to do the same thing. We're going to figure out 1 mole at these conditions has what volume. And our gas constant, we can fill that one in as well. Awesome. So now let's go ahead and plug it in and solve for it. So PV equals nRT. Since we're solving for volume, let's go ahead and get rid of pressure. So volume equals nRT over P. Oh, I missed one thing. So we have to make sure to convert our temperature. Sorry, backtracking a little bit. So 85 plus 273.15, 358.15. Again, you always have to plug in Kelvin. So we make that assumption of 1 mole. The universal gas constant, liters ATM per Kelvin mole. The temperature is 358.15 Kelvin. And the pressure, it's already an ATM, so that is good to get plugged in. Let's go ahead and plug that whole thing in. So do the whole top. 1 times 0.0821 times 358.15. Close parentheses, there's our top, divided by 12.4. And we get that the volume is 2.37 liters at ATM. So now this number is actually going to become our conversion. So that means that 1 mole at these conditions is equal to 2.37 liters. So that's not that 22.4. It's much smaller. So keep that in mind. So now we can start our conversion. So we're going to say always start with what you're given, same as before. So we have 55 grams of O2. If you have grams of O2 up top, it's going to the bottom. We're going to moles first so that we can switch compounds. Anytime you see mole over gram, you're always going to use that molar mass, same as always. So 1 mole. Oxygen, one of them is 16 times 2 gives you 32. Moles of O2 up top means it's coming to the bottom. Our next step is switching compounds. Now that we are a mole, we're able to switch those compounds. Anytime we see mole over mole, we look to the balanced equation. So next to O2, there's nothing, so it's assumed to be 1. Next to H2O is a 2. We keep on going. Moles O2 up top means moles H2O on the bottom. We're going to liters of H2O. So this is where we're going to be using that conversion that we came up with when we're going from moles to liters. So we assumed the 1 mole is equal to 2.37 liters. So all those units cancel top to bottom. You're left with liters of H2O for your answer. Now let's just plug it in and get our numerical answer. So plug in the whole top, 55 times 1 times 2 times 2.37, close parentheses, there's our top, divided by, open parentheses for the bottom, 32 times 1 times 1, close parentheses, hit enter, and we get 8.15. So 8.15 liters of H2O.